We're going to learn section 3.1 today, beginning chapter 3, and we're going to take all of that fun derivative stuff and apply it some more. Kind of what you knew how to do a little bit in math analysis, but now with calculus, so it makes it even more fun. Okay, so our objectives for 3.1 are we are going to identify relative or absolute extrema. So that's talking about our max and our mins. And that's the main goal for today. So we can also talk, though, about where a function is increasing or decreasing using the first derivative. Okay, well, let's first just talk a little bit about this graph. So here I can see that I have some relative max and mins going on. Relative just means in this little local area, okay? So if I look in this little local area right here, and if I was just to zoom in on that, let's do that. Woo! Again, I can't zoom in that far. Okay, so I was just to zoom in and zoom in right there. Okay, then I can see that this point right here is the maximum in that local area. So this is definitely a relative max. Let's zoom in and zoomed in on this area. Then min. And then on right here. You can see that relative. Alright, there we go. So here I have relative extrema. Now the thing too about this is that even though they're all little local or relative extrema, again, here I'm going to write that word local up here, because that means kind of the same thing, local or relative. Okay? Going on, they can still be the absolute extrema. So if I talk about the absolute max, it means the output going on, whereas it's the greatest on the entire graph. And here I can see that that output is going to be the greatest. So not only is this a relative max, but this is an absolute maximum. Okay? Is this the absolute minimum, though? Kind of look at where this output is. That right there. Is that the absolute minimum output? I hope a lot of you are saying, no, this goes down forever and ever and ever. So basically, if I'm going to talk about my absolute min, it goes to negative infinity. So I don't really have one. Okay? So that's the difference there. So here's just, again, some definitions. So the absolute max or the absolute min is the very most minimum value. And remember, the minimum value is the output. Or the maximum value, that's an output. That's a y value. Okay? So it means that it is the biggest y value or the smallest y value. Whereas relative just means on some little interval, some little local spot. Okay, so relative is just in that little spot. So again, when we were kind of talking about the graph that we had a little bit ago, we had an absolute, which is also a relative, but then this one was just a relative. And this one is just a relative min. Okay? So it's just within some little interval going on that you're zooming in and saying, oh, within this interval, that is my max. within this interval, that is my min. So those are relative. So some terminology to make sure we're good. If I'm talking about a maximum or a minimum, you don't have to say absolute. That's inferred. So if all you see is maximum, it means the absolute, or the global, meaning everywhere on the graph, the whole kit and caboodle. Over here, the relative is also called the local max or min. Okay, so you can write anything that you need to summarize here a little bit. So summarize in your words. And you can pause me for a second and go ahead and do that. Okay, now that you have unpaused me, let's look at this. So a lot of times students are like, do I write the point? Do I write the x value? Do I write the y value, the output value? So here, if it's talking about where it occurs at, that's the x value that it occurs at. If I want to know what the value is, that is a y value. And if I just ask you for a maximum or minimum, then this is a point with the x and the y. Okay, so this is important that you know, because if you write the x value, even though it's the correct x value where it occurs, it may not be what I'm asking you. I may want the y value. So make sure you can identify what it's asking for. Okay, yay, a theorem! So the extreme value theorem. It says if f, the function f, is continuous on a closed interval, so it's closed from a to b, then f has both a maximum and a minimum. So what was the condition for this theorem? It has to be continuous. So here are just some examples where I have a continuous graph, and here when it says a max or a min, it means the absolute again. We don't say absolute if all I say is max. And let's look at this first one. Here's a continuous graph. There's the absolute min. There's the absolute max. Here's a continuous graph, and again, it's on a closed interval. Okay. Here is the absolute max. Here is the absolute min. Closed intervals, absolute min, absolute max. So before we were seeing that the absolutes only occurred at humps, right? Back on that other page and all of the max and mins, but now I'm seeing that, hey, maybe they're going to occur at an endpoint. So at the hump or at the endpoint. So can you think of a graph that's continuous and it's on a closed interval a to b? Can you maybe just kind of think of one from a to b where it wouldn't be, where you wouldn't have a max or a min? The one that I would challenge is maybe it looked like that. Okay, so that output right there is both the max and the min. So it's actually at the same value when it's a constant. So you still have a max and you still have a min, but it's the same value. So it's just kind of boring. So looking down at these, here I could see that if I had this open circle, I am approaching a max, but I never get it. So that's because it wasn't on a closed interval. Okay. And here again, it's not on a closed interval. So it has to be continuous on the closed interval to have the max and the min. And here I actually have a min going on. Maybe it even, instead of going down, it looked something like this. So you could still have a max and a min when it's not continuous. The theorem just says that if it's continuous and it's closed, you're guaranteed a max and a min, meaning you will always have one. Whereas I could have so many examples where it's not continuous and I never have one. Okay, so these relative extrema are going to occur only at the peaks or valleys, the humps. My humps, my humps. Okay, so here I'm going to just have relative extrema where I have a peak or a valley. Kind of however you want to talk about the peak of the mountain or the valley going on in between the mountains. I just kind of say at the humps, at the turning points where you're increasing to decreasing. Okay, and these are going to be called some critical numbers. And if I kind of look at that, let's think back to when we were doing all the slopes, when we were talking about derivatives, all those tangent lines. So the first derivative, remember, gives me the definition for all the tangent lines. So what do you notice about any hump and its tangent line? What do they all have a slope of? Yeah, they all have a slope of 0. So basically, this is pretty dang cool. If I want to find some critical numbers for max and min, then I'm going to set the first derivative equal to 0, or I'm going to find where the first derivative does not exist, because that can also be a critical number, and we'll see that as we go along. So these are how I find my critical numbers. Okay, so again, for relative extrema, we're going to find where f prime of x equals 0 and f prime of x does not exist. Those are for relative extrema. Now for absolute extrema, you have to include one more thing, and that's the endpoints of the interval. Okay, so if you have endpoints, those are also. So absolute extrema, thank you, sir, are going to occur where f prime of x equals 0, f prime of x does not exist, and the endpoints. So you want to check for these as much as you can, okay? And those are all going to be the critical numbers for your extrema. Absolute just has the endpoints. So once I find all of my critical numbers, okay, so that's my first step, to find the absolute extrema or the relative extrema as well, okay? But for the absolute extreme, I'm going to get all my critical numbers, and I can put them in the original function. The smallest y is going to be the min, and the largest y is going to be the max.